So today we will study the reaction turbine. Reaction turbine. So here it is already written that the relative velocity, outward relative velocity is less than the inward relative velocity, whether its bed is frictionless or frictional. So here we can see the velocity diagram. So velocity diagram is somewhat different from the reaction turbine. Okay, if we want to study this, let us draw the velocity diagram of the reaction turbine uh, separately. As we have seen that this is the velocity diagram of the impulse turbine. We have drawn from this to this velocity diagram. So it is somewhat same with the impulse turbine. The velocity diagram of the reaction turbine is somewhat same with the uh, impulse turbine. So what we should try to understand what are the differences of the velocity diagram. Everything is same. Everything is same. Let us compare both. Hmm. This is the velocity diagram for impulse turbine, and this is for reaction turbine. Okay. So here we are seeing that this is the blade velocity, and this is the relative velocity of inward steam, and this is the relative velocity of the outward steam. So here what we are seeing that here the axial momentum, axial velocity is because of uh, axial velocity is more than axial velocity of the outflow is more than the is less than the axial velocity of the inflow. So there is a axial force applied on the blades. There is axial force applied on the blades of the reaction turbine. So here this is becoming the resultant force. Why? Because this is the axial force applied on the blades, and this is the tangential force. So this becomes the resultant force. So resultant force is somewhat tilted from the tangential direction. It means that there is a application of the axial force applied also in case of reaction turbine. Okay. So what we are seeing here that here it is showing one more line which is called impulse. This is the impulse effect. So impulse effect comes to a point like VR2 comes from this to this. VR2 is here more. Relative velocity is more. And while relative velocity is more, we should try to understand this. We will study this further in detail. So relative velocity V2 is more. So up to this point, it is giving the impulse effect, and this is the reaction effect. So what I'm trying to explain here is that if we have the tangential force from this direction, so it is coming from the net effect of the reaction force and plus impulsive force. We are getting the tangential force. No, no, no. Sorry. We are getting the resultant force. We are getting the resultant force with the help of the sum of reaction force and impulse force. So we'll try to sum up some of the points here AB is equal to BC. AB AB is equals to BC. AB is the impulse and CD is equal to reaction. Okay. It works on the principle of impulse and reaction, and it is just reverse of axial flow compression. Yes, of course. Reaction turbine works on the principle of the reverse principle of the compression, and each stage consists of fixed and moving blade, and the blade passage is made converging both for fixed and moving blade. Yes, there is a drop of pressure in the fixed blade due to which absolute velocity increases. There is a further drop of pressure in the moving blade due to which relative velocity increases. So this thing we should try to understand that what is explaining here that uh, there is a drop of pressure in the fixed blade. In the fixed blade there is a drop of pressure because it is somewhat converging type. So pressure drop occurs due to which absolute velocity increases. Absolute velocity increases. There is a further drop of pressure in the moving blade. Now again in the moving blade, drop of pressure occurs due to which relative velocity increases. Now relative velocity also increases here. Okay. Total work is obtained in the moving blade due to combined effect of impulse, that is V1 square minus V2 square by 2, and reaction effect, that is VR2 square minus VR1 square. Okay. So here we have the inlet energy V1 square by 2, V1 square by 2, and VR2 square minus VR1 square by 2. This is our inlet energy. This will be our inlet energy, and the blade efficiency we'll try to find out. This that will be because of the turbine, the work. I mean, in case of the turbine, work we are getting, or we can say the work rate or power we are getting VW1 plus VW2 into U, that energy got from the moving blade, and this is the inlet energy given to the moving blade. Okay, then we'll simplify that. We are getting this blade efficiency. Okay, so this is different. This is the extra work is applied on the moving blade. We have to square one, we are square by 2. Hmm. Uh, in case of axial machine, if it is axial flow machine, then the area will be area. This is the radius of the rotor, and this is the radius of the hub. Like in case of axial flow turbine, it is somewhat like this, 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 this. So this is the thickness of the, or we can say that this is the radius, RT radius of the blade, and this is the radius of the hub. So the effective area will be the pi RT square minus RH square, or we can say the pi by 4 DT square minus DH square. Or area will be pi dm h. Here is the main diameter. Main diameter. It means that we can say that dm will be dt plus dh by 2. And what is capital H? Capital H is actually dt minus dh is capital H, which means that dt is equal to h plus dh. This is dt. This is the diameter of the hub, dh, diameter of the hub, dh, and when we add the height of the blade, h and h here, so we'll get the whole diameter dt, tip diameter, blade tip diameter. Okay. Now we'll study the Parsons reaction turbine. What is the Parsons reaction turbine? So in actual working, 50% reaction stage is preferred as the blade design and manufacturing. Because of the easiness of the blade design and manufacturing, 50% reaction turbine is preferred. Efficiency obtained is near optimum and axial thrust of the rotor get neutralized. Axial thrust of the rotor get neutralized. We are not getting any axial thrust. So it is very good for the health of also the turbine. So we are getting like this. So here we can get some relation like theta will be equal to beta. It means that the uh, inlet blade angle will be equal to the angle of the steam that is flowing outward from the turbine, and alpha is equal to 5, that is the outlet blade angle will be the incoming steam angle. Okay, and here v1 is equal to vr2 and vr1 is equal to v2. Like this, from the symmetry we can relate these relations. First draw this diagram and try to find out this reason. And now vf1 is equal to vf2, so there is no axial thrust we are getting. Let's calculate the condition for the maximum blade efficiency like we have calculated in the impulse turbine. So the blade efficiency we have got this. Now to find out the maximum blade efficiency, we have to convert all these manipulations like VW1 we can get from the diagram V1 cos alpha like we have done in case of the impulse turbine. Similarly, we can also manipulate all these relations here like VW1 is equal to V1 cos alpha, VW2 is equal to VR2 cos phi minus U, and VW2 is equal to V1 cos alpha minus U. So from that relation, we can get the optimum rho optimum, that is the ratio of the blade velocity to the steam inlet velocity. Rho optimum is equal to cos alpha. But in case of the impulse turbine, we were getting cos alpha by 2. Rho is equal to cos alpha by 2. Okay, and maximum difference is equal to 2 cos square alpha upon 1 plus cos square alpha. Okay, so we can let's see the what are the differences with respect to hmm, impulse turbine. Hmm. So here rho optimum we are getting cos alpha by 2, that is 2. 2 is involved here. 2. Here rho is equal to cos alpha by 2 and maximum blade efficiency is equal to cos square alpha. If cos square alpha, if x is equal to 1 and k is equal to 1. Okay, this is cos square alpha and this is this. So we can say that blade efficiency cos square alpha, and in the case of reaction turbine, in the case of reaction turbine, if you are seeing that, so here we are getting blade efficiency 2 cos square alpha, which is more upon 1 plus cos square alpha. So we can see the differences. What are the differences between the impulse and reaction turbine? So in case of impulse turbine, reaction turbine. So in case of impulse turbine, blade is symmetrical. Theta is equal to 5. Reaction turbine blade is unsymmetrical. Like here, we can see that the inlet blade angle is greater than outlet blade angle. Theta is greater than 5. Okay. Pressure and relative velocity. Pressure and relative velocity. So Inlet relative velocity is greater than outlet relative velocity. In case of equals. Here, inlet relative velocity is less than outlet relative velocity. Here, relative velocity increases. In case of reaction turbine, because we have to find out, we want to get the reaction effect in case of reaction turbine. So the outlet reaction velocity should be more. Okay, that's the pressure drop occurs because of the orientation of the blades, because the aerodynamic shape of the blades, we are getting the reduced pressure, and because of that, the velocity is increasing because it's working like a nozzle in case of moving blade. Okay, inlet velocity is v1 square by 2, but in case of reaction turbine, the inlet energy is more v1 square by 2 plus v2 square minus v1 square by 2. And optimum, rho optimum for the case of maximum efficiency cos alpha by 2, and here only getting cos alpha. So we can see that the efficiency is more in case of reaction turbine. Okay. No, 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 sorry. In case of efficiency is more, rho optimum is more also for reaction turbine. Here only cos square alpha, and here 2 cos square upon 2 cos square alpha upon 1 minus 1 plus cos square alpha. Okay. So in case of impulse turbine, the efficiency is cos square alpha, and for reaction turbine, 2 cos square alpha upon 1 plus cos square alpha. Okay. We can also solve some questions. I will show you. You can pause and solve it. Okay. These questions you can try. I will show you the question in some other lecture. These are the solutions of this question. But you don't need to copy it. You can try it from the previous year questions. Hmm. So we'll further study the next topic. Let's stop.